and that is that you know that we're trying to solve advection dispersion equation. You know exactly what it is now, I think. Minus advective velocity, dc dx. And you know that this term here, and there's also a transverse dispersion term as well. And so it's for flow in the x direction versus y. And we talked about this last time, that this is longitudinal dispersion and lateral dispersion. And what was this? This is equal to diffusion, which is called d star. Mechanical dispersion times advective velocity. This, I suppose, we called before some tortuosity coefficient and fixed law value of diffusion coefficient. And we went through last time to talk about how we might get this from experiments. And we actually came to the realization that you could get this from the length of the plume divided by 10. And I said earlier as well, the transverse is maybe a third of the longitudinal. So the comments from doing an experiment in a core and trying to fit the data works fine so long as it's diffusion dominated, but it doesn't replicate the kind of large scale structure of the porous medium, which is really what this term is, and it's important to know that. So it works well if it's diffusion dominated. So if you want to know what the diffusion coefficient is in bentonite that you're going to use in a nuclear waste repository, then that might be a good way to do it. You could do it by injection in a single well and pump back out and see what the residence time distribution is. Or you could do it in an injection and recovery well that we talked about, twin wells. But that doesn't work very well because it has some dispersion, which is just a geometry of the flow system, which is completely unrelated to the material property. And also it uses a gradient which is much higher velocity than is in situ, and therefore doesn't return very good values for that reason, perhaps. And the best way to do it would be to use a natural gradient test. And those results would look like this. And the reason that it's important to do that is that, or the reason that we can also get it just from the size of the plume is because as a plume gets larger and larger and samples a bigger volume of the aquifer, then it has a bigger chance of finding a fast flow channel. So we talked about that. So everything to date has discussed this advection dispersion equation. We always note it in terms of the concentration. But the other thing, I guess, which I mentioned when we parted yesterday or Tuesday, was that if you look at the behavior as you go down gradient, the easiest way to show this is that the area, if it's conservative, so-called conservative, then the areas under each of these curves should be the same, because it has the same amount of mass that's in each of these. And I guess in this case, the area under the curve would be in 3 dimensions. It'd be the dimension into the page as well. It'd be the volume under this curve. And this is concentration. And necessarily, the peak of this goes down as you go downstream because it's spreading out wider, and so you'd expect that. And so that's the case for what we'll call conservative transport. And that's what we've talked about so far. And so what we'll talk about now is non-conservative transport. Liberal transport, I could call it, perhaps. Ha-ha. I think. So the consequences of non-conservative transport are these two things. Retardation, which means a delay in arrival. And attenuation means lower concentration. At arrival. And so we've kind of seen a bit of that before, right? This is lower concentration with arrivals that go down, but this is because it's spreading out. When we're talking about attenuation due to non-conservative transport, we mean that it gets bonded onto the porous medium, which isn't moving, so the water moves past it and it relinquishes some of its mass, dissolved mass, onto the solid substrate, and it results in these two components. And it can occur because of chemical reactions or sorption. We'll talk mainly in terms of short sorption, but it can also occur because of chemical reaction. Figure out how we might measure it using natural gradient experiments or other. And we can also talk about sorption-like behavior, which we get in fractured rock. And yeah, I guess this is the statement. So we know what the advection dispersion equation looks like as we go downstream. Great, greetings. We know that how we apply our boundary conditions and what happens in the aquifer is controlled by dispersion. Plug flow and the maintenance of a skyscraper means there's no dispersion. If it gets a shallow front, it means that dispersion is larger, I guess, is not equal to zero on the red curve here. And so if we look at reactions, there are a whole bunch of different reactions you could imagine that occur. Adsorption and desorption is the main one we'll talk about, but you can imagine all kinds of reactive processes that would transform different components that are dissolved in the fluid into other compounds or result in them changing their concentration. And I don't want to spend so much time on it. It's really quite a simple idea. And the idea is this, that if you look at our advection dispersion equation, then we know that this is accumulation. And we know that this is basically mass in minus mass out, dissolved mass. It's just a continuity relationship, mass balance. What we could do is we could add a couple of other terms, which would be a reaction of components that are going downstream, or perhaps easier, we won't really talk about this, but perhaps it's easier to talk about sorption. And sorption would be stuff that's dissolved in the water that gets attached to the quartz particles in the aquifer. And we can define that behavior in terms of a density of the aquifer, kilograms per meter cubed, a volumetric moisture content. So the maximum limit of this, if it's saturated, would be the porosity. It's written in terms of volume of pore space per unit volume of the aquifer. And the concentration of the solute that's sorbed per unit mass of the aquifer. So this is the amount that's removed from water and plastered on the solid per unit time. So if this is removed from the flow, the fluid regime, then it's also kind of an accumulation term, or a negative accumulation term, because it's being removed. So what we could do is we could try and figure out exactly what this term is here, how much gets removed per unit time. And the easiest way to do that is think of what sorption is. So sorption means that if you take a beaker, and that beaker has a bunch of grains in it, which make up your porous medium, and you put in some fluid that has some concentration C, which we've used before, then you can imagine that some of that concentration will bond onto the surface of the grains, and that's what we're exactly calling C star, the amount that is removed from. Obviously, if C star gets attached on the grains, if you empty the water out, it's not present in the water, and so you're changing the concentration by de facto in the water as a result of that. So when we look at sorption, if you pour this fluid in at some concentration into a beaker and look at how the concentration changes with time, isotherms are always the steady state. So it takes a certain amount of time for it to get up to that behavior, and then after that, for all time, nothing else happens. It sits there, it's in equilibrium until you add some more, a higher concentration. If you then add double the concentration in here, then this would change to another magnitude. And actually, if it's a linear system, the concentration on the solid would be double the amount. And so that's what we are talking about. So a sorption test is exactly when you do that. You add something to a solid, you look at how the concentration changes either on the solid and reciprocally in the liquid. If it goes onto the solid, then it has to come out of the liquid. And then we make those measurements. And so what it would do in time is what is shown in that figure above. But if you measure the concentration relative to the concentration, this is aqueous. This is solid. Then if you do this first experiment and you add it, then it will partition onto the solid with a data point here. If you double the concentration, you add it, you'll get another data point here. And so linear sorption means just this. And I guess you could think of this as this would be dC, and this would be dC star, a small increment of those. And so if we're interested in writing our expression in terms of a concentration on the solid changing with time, we could also write this as, I'll do it in red. You've seen this done before, this kind of little trick. If you multiply top and bottom by dC, then you've just changed it. And so this, if we're using this equation here, we'd like to be able to swap this into a value of dC dt, because our equation is written in terms of aqueous concentration throughout. And so to do that, we can just use this little construct to multiply both top and bottom by dC, and we've got this. And so by definition, this term is this isotherm, just the gradient of this line. So that's what it is. And so we call this term the distribution coefficient. Uppercase K sub D equals distribution coefficient. And hopefully it's something we can measure somehow. And so if we take that as being some parameter we can get, then let's go back to, well, this just explains this. So this distribution coefficient is just, K sub D is just equal to C star over C, or just the increments of those, if you like. I guess we called DC, for some small increment of each of those. It can be linear, it can be nonlinear, Freundlich isotherm. Langmuir isotherm is often used as well. You must have seen these in your past. It just means that as you increase the concentration, each of these points here, I guess it serves to note, would be the same as this one point here, right? You add it, it takes a time to come to equilibration, but once it's at equilibration, it's at that C star for all time. And so this represents one data point that would go on the isotherm here. So you do it multiple times, you wait for it to equilibrate, you take that one measurement. So what this means usually is that you filled up all the sorption sites on the surface of the mineral, and there's no more space for something to go. So the concentration stays the same. You filled them all up. And so it means that you've reached saturation of that particular compound. So what we'll use primarily is linear isotherms, just because it's good enough for what we want to use it in. They're in interesting units. Some of them are mass per unit mass sorbed per unit mass of the aquifer. Some of them are in mass per unit volume, mass of solute per unit volume of the fluid in the aquifer, and volume per unit mass, just from the terminology, right? It has to be, if you know what the magnitudes of each of these are, then by definition that gives you a distribution coefficient in a volume per unit mass. Okay. So our interest in doing this is we'll ignore this. We'll take this term here, we'll multiply both top and bottom by dc, I guess partial dc, right? And so that we get this. And if we do that, then all of a sudden this is written in terms of this. And so we can move this term by subtracting it off to the left-hand side. That's what we're doing here. And so we end up with, if this is the equation here, then longitudinal dispersion, add vector velocity, this and this on the left-hand side. This is just multiplied by 1, and this is density, porosity, as if it's saturated, and the distribution coefficient. That's all. And so this is referred to as usually R. It's called the retardation coefficient because it tells you how long you have to wait for the front to arrive, because it takes longer. This is always positive, so it's always between 1 and infinity. Typically it might be between, it's always greater than 1. It's typically maybe 30 times slower than it would do otherwise. And so we can write our expression in terms of this. So I guess our advection dispersion equation would be, this term here is just R multiplied by this, which you've seen before. And I guess it might also have the transverse dispersion term, if we wanted to include that. It's written in terms of concentration, liquid concentrations throughout, so we can rearrange it. Divide both sides through by R. And this is 1 over R. So this whole term here goes to 1. And we have this. And so this is useful because it essentially, from what we know about how the advection dispersion equation works, it tells us exactly what we might expect for the effect to be manifest. And so what it is, it's dividing our advective velocity through by some number bigger than 1. So what it means is that if our original, this is conservative, this would be 1 pore volume. So T sub r equals 1, right? In other words, the advective velocity times time would be the length traveled, which we've used before. So this would be, and that's 50% concentration. So what we understand by the advective component is it means it's traveling at that velocity divided by r. So the length traveled in a given time would be just, instead of vt, it'd be vt over r. So it means it would travel that much less far in that time. So that's the advective effect. So the dispersive effect is that it's also reducing the effective dispersion coefficient by the same magnitude. And so we know that the effect of the dispersion is that it, if you like, it softens the front. So if it was plug flow, this would be an infinite dispersion coefficient. A finite dispersion coefficient would be flatter. And so if it's reducing this, then it means that it sharpens the front. So it may seem surprising. So it has two effects. It means it travels less quickly downstream, and the front surprisingly gets sharper because of its influence on each of these things. The other thing is it suggests is that since all of our calculations we've done so far have been with this advection dispersion equation, we can use exactly the same solutions that we've talked about, but we just have to modify the values of the coefficients by these terms. And we know that the coefficients are 2, right? The Peclet number is equal to the velocity times time divided by dispersion. If we see that the terms in here are pre-divided by these magnitudes, then velocity has to be divided by r, dispersion has to be divided by r, and so the effect is that the advective velocity is unchanged. If we do the same on our pore volume term, what we've called TR, or Courant number, I'll do it down here because I've run out of space. What is it? It's velocity time over L. Yeah, I guess it was L. And if we do the same treatment to this, velocity is divided through by r, but none of the other terms are. And so the TR term will be changed to be velocity time over RL, which is actually kind of what this is here, right? It's divided through by this. So we could use any of the one-dimensional equations we talked about before, but we'd have to use a Peclet number and a pore volume number modified for the fact that we have retardation. If it's equal to 1, then these terms revert directly to the conservative terms, and if it's not, then we have to use the non-conservative. So that means we don't have to reinvent the wheel in figuring out how to do these calculations. So, yep, hit me.
So I understand the return to velocity, that makes sense because you're absorbing that.
Yep.
So it actually reduces the dispersion, so like it doesn't disperse as much when it gets.
Yes. Is there a question there? That's a statement. Is there a question why?
Yeah.
Because I think probably, good question, if it was not being retarded, not being delayed, it would look like this. Not very good. So if you forget the fact that it's being moving slower, if this was the case where it's not, if you imagine it's a conservative solute, then it has this amount of mass ahead of the front and this amount of mass behind it. But this is actually traveling more slowly. And so if it's traveling more slowly, then it's not going to get so far ahead of the front. I think that's probably the reason.
Yeah, so
Seems
part of the reason that
seems counterintuitive that it would get sharper, right? You
Yeah,
might
so-
think it would spread.
Yeah, so basically the fact that the overall system is moving slower in
Slower.
general also slows down the amount that we can mechanically disperse, basically.
Yeah, that's right. So, what else do we want to do now? Well, we want to use Sean's wisdom of summarizing last class, that none of these methods work for either laboratory or in situ testing except for the natural gradient tracer methods. And so maybe we could go back and figure out how we could use this to be able to figure out what these distribution coefficients would be. And so one way to do that is to do the thought experiment, where now at Borden, Canadian Forces Base Borden, you put something in the ground, and actually it was a cocktail with more than one substance in it. The one we looked at before was the chloride ion. Probably sodium chloride was put in the subsurface, which is not reactive, which is conservative, and traveled in 2 years, it traveled 57 meters downrange. But at the same time, what was put in was carbon tetrachloride as a solvent, and also tetrachloroethylene, PCE. And the same thing was done, that these were measured, and their progress of the clouds going down range were measured at each of these same intervals. These people came back on site after 600 days, 360 days, and 16 days roughly, and did these assays. And so these are all those three results shown on one. Chloride, dissolved carbon tetrachloride, and PCE. And so they've all gone different lengths downrange. I guess we could note that the velocity non-conservative is equal to the velocity conservative divided by r. Kind of, right? If you agree. This is here. So this would be, this is the non-conservative velocity, which is the VC divided by R. And so we could rearrange that to give that the retardation coefficient is equal to VC over VR, VNC rather. Is that right? And we know that VC is equal to length C over time C, and V non C is equal to length non C over TC, TNC. You take them at the same time, so TC and TNC are the same, they're equal to 1. And so this is length C over length non C. And so you can just use these ratios of lengths, and it makes sense. R is always bigger than 1. It travels longer when it's non-conservative. So in this particular case, the retardation factor for carbon tet is equal to 57 meters over 28.5. Which is about 2, right? And the retardation for PCE is equal to 57 over 13. Which is about 39, about 4, right? Something of that order. And so we can get the retardation coefficients directly from that. I suppose if we wanted to also, I'm running out of space, and I think I'd do the same calculation down here. I don't need to write it out. So immediately, if we have experimental results like this, we can determine what the retardation is. If we know what the retardation is, we can do modeling to project behavior to go beyond, to find out where the plume will be in 10 years' time, 20 years' time, and what the concentrations would be just by using this expression here and doing forward modeling. We could also, if we wanted to, convert the magnitude of the retardation coefficient into a material property, which we decided was the distribution coefficient, which is here. And so if we know what the value of R is, which is this circled or ellipsed term, we could solve for the value of KD because we know pretty closely what the bulk density and the porosity are. And so that's all that's being done here. And so if we take our definition of retardation coefficient, if we rearrange it in terms of distribution coefficient, we get this. And we can just try and calculate exactly what this value is from the value of the retardation coefficient that we got. So I guess the values, was it really 1.4, not 2? I guess this is 30, and this is almost 60. It seems... Did I put down 28.5? 23.5, right? Yeah, fine. So that's the reason for that. So it's 2.35 or something. But same idea. So didn't need to do that. So if we take these values that we have, was it 1.42? Yeah, okay. So this is 2.42 minus 1 is 1.42 multiplied by these terms. This would typically, and actually for this particular site, is 30%. It's saturated, so n is equal to 30%, but it's a decimal in this case. It has to be a decimal. Bulk density is something like of soils or rocks is 2,000 kilograms per cubic meter. And so if you look at the units of this term, it's kilograms per liter or grams per milliliter, however you want to put it in. And if you do this, you end up with a value of distribution coefficient, which is in liters per kilogram. And that we don't have anything else to do with that yet. What we'll talk about next time, we've still got one more slide to do today, it might be a short class. We'll talk about how you can get this distribution coefficient, KD, directly from chemical coefficients. It turns out that in lots of aquifers, the main item that sorbs stuff is organic carbon. Just like you put stuff through an organic carbon filter to take out solvents that are dissolved in liquid. In an aquifer, if you have organic carbon as part of the aquifer, that's the main source, the main sink that these components will go into, and it's the main component that makes up this distribution coefficient. So if you know something about the type of solvent that's dissolved in your water, and you know the mass of organic carbon that's present in your aquifer, you can make a pretty good estimate of KD by assuming that the only sink of the sorption is onto the organic carbon and ignoring the stuff that goes onto the grains. And that's what this stuff down here is about, comparing the estimates of KD from those methods, which we'll talk about next time. So we can do that. So we've been able to get magnitudes of retardation coefficient from looking at natural gradient tests. We can get values of K sub D, which represent that behavior as well. So we're almost done. I guess the last point I wanted to make is you can get some behaviors that look a bit like sorption from things that aren't sorption. I suppose just like we said that we can get behaviors that look like diffusion but aren't diffusion, they're dispersion, mechanical dispersion. But as you look at them, they just appear to be. And that is by looking at behavior in fractured rocks, porous fractured rocks. So if you have a fractured rock that has an impermeable wall rock, and you put a solute dissolved into it and push it downstream, you get a distribution in the aquifer which might look like this. A sharp front, a uniform concentration on everywhere behind that sharp front, which is just what this is representing. If you took samples along the length in space at one particular time, you get exactly that behavior here. If instead of making this zero porosity, you give it a porosity and you fill that porosity with water, then some of this solute can diffuse into the water, maybe by mechanical mixing, but also just by Fick's law, Fickian diffusion. It's been in contact the longest time upstream, and so it's traveled furthest and removed most of the mass in this direction. And so now if you took the concentrations along the length of it, it would look like this. And so this behavior here, instead of this, is exactly the same as comparing this red curve and this red curve. And so there's no sorption occurring in this. You're getting diffusion and loss of mass into the porous medium, but it looks for all intents and purposes like this. If in addition to this you get diffusion into the pore space, and then on the solid grains of that pore space some of this solute attaches itself and sorbs, then that's also removing it from the flow and allowing more diffusion in the pore space, because you're reducing the concentration, and therefore you'd expect along this component to get an even more noticeable delay in the plume as it goes downstream. So there's, I guess this, technically this has sorption involved in it, so this is sorption, but between this one and this one, there is no sorption. There is, I guess, just diffusion. So merely in the same way that mechanical dispersion looks a bit like diffusion as you see its effects, and we characterize it as an effect on this diffusive term, right? When we look at the advection dispersion equation, this is the diffusion term. We label it with an effective diffusion. Didn't do that very well. Effective diffusion here. But this is actually components of diffusion plus dispersion. And so we know that, we account for that here. The effect of diffusion and dispersion are mixed. Usually one dominates, but regardless, the form of the resulting concentration distribution is the same form, either whether it's diffusion or dispersion. And in this case, that's the only case we're making here. That in this case, it looks like it's sorption that's occurring because it's been delayed. It hasn't been sharpened, I guess, in this particular case, but it's been delayed. And therefore, we can get the effects of sorption-like behavior, but in this case, it's only by diffusion of the mass within the water that's populating the stagnant pores of this particular porous rock. And that's it. Won't talk about the rest. That's it. So it's obvious that a key parameter we need to get is this distribution coefficient. So if you don't have a readily available natural gradient test to be able to recover the retardation factor from, and therefore get this, then you have to do it some other way. And the easiest way to do it is just by looking at the amount of organic carbon in the aquifer and go after that. And we'll talk about that next time. Ways of being able to do this, either based on the octanol water partition coefficient, or it also scales with the solubility of that particular compound in water as well. So we'll talk about that next time.